In large projects, the process of compilation becomes so significant that it's referred to as building the project rather than merely compiling it. Software to track and manage the build process exists in many forms on many different platforms. The main tool for Unix build management is Make, the subject of this lecture segment. You need to understand the compiling and linking process in order to understand what Make does. If you're not sure what an object, a .o file is, or what the linker does, or what types of errors might occur during linking versus compiling, or why you don't need to recompile every .c file in order to recompile a whole program, then you need to review the prior lectures on multi-file C compilation, Lander 9, for example. So assuming those concepts are well in hand, then let's talk about build dependencies. Any complex C project comprises many C source files and header files. Recompiling all the source files anytime a change occurs to just one of them is prohibitively time-consuming. Selective recompilation of source files is essential, and keeping track of which files need recompilation due to a change and which do not can be very complex. Different C source files include different headers, and of course headers may include other headers, so a source file can include headers both directly and indirectly. Any change to a .c file or to its headers means that the .c file must be recompiled, and the entire application relinked from object files. In a typical large project with 1,000 C source files, a minor change to one header might require recompilation of 500 of those files, while changing a different header might require recompilation of only one file. Determining by hand which files are affected by a change is practically impossible, and of course error-prone. Missing even one needed recompilation would leave an object file that was compiled using an old version of a header or source. The bugs that result from this can be very subtle. So, every large software project uses some program to track build dependencies, such as the dependency of a .c file on the headers that it includes, or that of an executable on the .o files that link together to make executable. On Windows or Mac, projects often use IDEs like Visual Studio or Xcode. On Unix, the tool of choice is Make. Make is simple to run. You simply give the command make and an executable, where executable is the name of the program you want to build or to rebuild. The make file in our example manages two executables, test.exp and test.cmp. To rebuild the former, we'd simply type make test.exp. But make is complex to configure. You must describe to it all the build dependencies in your project, all cases where file X must be rebuilt if file Y is changed. And you must tell it how to rebuild X. All this is done via a make file, a textual configuration file describing dependencies and rebuild commands. The make file is named either capital M makefile or lowercase makefile. Make automatically looks for either file name. The capitalized version, by the way, is convenient because it usually appears before other non-capitalized files in an LS listing. The makefile format is very 1970s. It's textual and has elaborate indentation and line continuation rules. And there's a good example here in the diagram. Let's start here with the first line. We start with a comment line marked with an initial pound sign. Any line or rightmost end of a line may be marked as a comment this way. Certain strings, such as lists of file names or command options, are often repeated throughout a makefile. So a makefile allows string variables. You don't declare these. You just put a value into them via simple assignment statements, as on lines 3 through 7 here, which create and assign variables CPP and CPP flags and so forth. Variable names are capitalized by convention. The value assigned is always a string, and there are no quotes. The entire rest of the line is assigned into the variable, spaces and all. The assignments must fall on a single line, though you may escape returns with a backslash in a fashion similar to that for multi-line C macros. and with the same caveat regarding escaping the return, not a space just before the return. In our example file, we set up a variable CPP with the command for C compilation, so that can be easily changed. Another variable CPP flags for the flags to apply to the C compilation, and then 2 for the lists of .o files that must be linked for the 2 executables LZW-EXP and LZW-CMP that the makefile is configured to build and manage. Now, to use the value of a variable in the makefile, you put the variable name in parentheses and a question or a dollar sign before them, like here, $ parenthesis CPP. Now, this seems really awkward if you're used to using a variable name directly in a programming language. The reason for the notation is that makefiles refer to many file names, command names, etc., all of which might coincide with variable names. Since the number of non-variable words is so large, it makes sense to require special notation to get a variable's value. And remember, make was designed in 1977. Now, the core of a makefile is its dependency rules, such as those on lines 9 through 16 here. These rules take the form target, and then a colon, and some list of dependencies, and then following that, one or more, actually technically 0 or more as we'll see, build commands. Target is generally a file that might need rebuilding. Dependencies is a list of files on which target depends, and build commands is a list of commands that must be run, such as compilations or linking, to bring the target up to date if any of the dependencies have changed. Make uses the last modification dates of the files in question to determine if a rebuild is needed. If any of the dependencies files were more recently modified than the target, or if the target doesn't yet exist at all, then make does the build commands. Lines 10 through 11, or 9 through 10, for instance, indicate that the executable test.exp is dependent on all of the object files in test.exp objs. If any of those object files have been more recently modified than test.exp, or we don't yet even have a test.exp executable, then make runs the line 10 command, which relinks all the object files to create a new executable. Replace all the various variables with their values to see what command is actually being run there. And here's in lecture question 1. Since we are running GCC, doesn't that mean we're recompiling as well as linking? And what does the GCC-O option over here do? Now, this question is mostly a reality check to be sure you recall or have reviewed multi-file compilation basics. Coming back from a pause there. GCC is actually a master program that runs the preprocessor, C compiler, and or the C linker, depending on the argument files. If you give it all .o files, it just links them. And if you want the executable to be other than an a.out, you give the desired executable name via the .o or the -o option. So when did the .o files get updated? The dependency rule on lines 15 through 16 controls the rebuilding of one of them, LZW-EXP.o. And as you can see, the rule rebuilds LZW-EXP.o if LZW-EXP.c has changed. The command to do so is another GCC run, this time to compile the LZW-EXP.c file. Here's another reality check question. What's the -c option for? And if you're having trouble doing these and you have to look them up, do the review lectures, Lander 11. Coming back from a pause there, the -c option compiles a .c file to a .o file without expecting a full program or trying to link anything. Now, to complete the makefile, we'd need dependency rules like the one for LZW-EXP.o for each of the other .o files. But in the next segment, we'll see several ways to generate these automatically. So let's let lines 15 through 16 be our one hand-built example. Each .c file is dependent on any header files that it includes, in the sense that a change to the header amounts to a change to the .c file. So a make file should have dependency rules showing this, as in the example for lzwexp.c on lines 18 through 19. The build command for this rule, however, is a little odd. If a .h file changes, the .c file including it automatically changes, and there's no action needed for that to happen. But we do want to show the .c file as having been modified so that it in turn triggers other dependency rules like that on lines 15 through 16. And the solution is the Unix touch command, which updates the modification times of any files given as command line arguments, showing them as modified at the current time, as if they'd been rebuilt, even though their content doesn't change. This command is surprisingly useful in Unix operations in general, and it's a good one to add to your repertoire if you haven't seen it before. The target in your make command, make of some target, must be one of the targets in a dependency rule, for instance, test.exp. Make checks each dependency in target's rule and rebuilds target if any dependency has changed more recently than target. But, a critical point, make also checks each dependency to see if it is a target of another rule and rebuilds the dependency if needed. And this applies recursively, as deeply as necessary. So, if test.exp depends on lzwexp.o, part of the string there, then if lzwexp.o also depends on lzwexp.c, and if lzwexp.c depends on, say, codeset.h, then if codeset.h has changed, this triggers a touch on lzwexp.c, whose changed modification time then triggers a rebuild of lzwexp.o, which thus changes, and in turn triggers a rebuild of test.exp. In general, if executable E is dependent on object file O, and O is dependent on source file C, and C is dependent on header H, then even if only H has been updated, this triggers a cascade of rebuilds, from H to C to O, and ultimately triggering a rebuild of E. The dependency rules don't have to appear in any particular order for this all to work. Make figures it out regardless of their order. Visualize a make run as starting at some target, and then branching out through all the target's dependencies and all of their subdependencies and all sub-subdependencies, etc., making a tree of dependencies. The make run then works back from the leaves of this tree, doing rebuilds anytime dependencies have changed more recently than their target. Any rebuild of a target A causes A's modification time to change, which in turn triggers a rebuild of any target B that depends on A, etc. Now, in some cases, a dependency rule is designed without the intent to actually rebuild the target. The target is usually non-existent in this case, and it remains that way. The rule on lines 22 through 23 here is a good example. There is no clean file, so the target always automatically needs rebuilding, even though there are no dependencies either. The rm build command cleans up temporary files that result from other compilations or links, and thus make clean is a way to clear any existing object or executable files. Following it with a make test.exp, for instance, would cause a complete recompilation, since all object files are gone. Since the build command doesn't update the file clean, there is none, you get the same effect every time you run make clean. Let's kind of wrap up with a third in lecture question here. The makefile example has two executable targets, test.exp and test.cmp, and that can trigger a rebuild of either with make test.exp or make test.cmp. I'd like, however, to be able to remake both of them with the command make all. Add a dependency rule that would do this, and don't be surprised if it's really short. Coming back from a pause, this can be done with a rule that would read all as the target, colon, test.exp, test.cmp. And there's no need for any build commands. Since all doesn't exist, the dependencies are checked for being up to date automatically. Doing this causes any needed rebuilds to test.exp and test CMP. And since once we're done, there still is no all file, it'll work the same way every time I run it. If you don't list a target after the make command, you just give make by itself, it makes the first target in the make file. And a target like this all target is often put first for that reason. In the next segment, we'll look at ways to set up dependency rules without having to hand write them for each source and header file.